All right, so next up we have Florent Hivert with machine-checked proofs and programs in algebraic combinatorics.
Thank you. Thank you for the organizer to allow me to talk. It's my first talk about proof in a wide conference, because I'm not at all a proof guy. I'm, let's say, computational mathematics guy, so I'm playing with algebraic combinatorics, I've been heavily involved in computer algebra development, such as SageMath. Actually, I coordinated the development of the combinatorics library in SageMath for a few years. And during that coordination, I had the opportunity to see how not so good the implementation was in terms of correctness. And that's a problem, because in algebraic combinatorics, we are always we are trying to prove algebraic identities using algorithm and data structure. But when I see how bad those data structures are implemented, I'm wondering about how bad or proof are they already correct? So that's what I wanted to investigate in this work. And today, I will present a relatively large library based on Rocq and mathematical components. So the library which was developed under the lead of Georges Gontier to prove the four-color theorem and the order theorem. And what I'm dealing with is about symmetric identities, about symmetric polynomials and character formula for the symmetric groups. So really computational question. And my flagship result is the Littlewood-Richardson rule. And I will try to give you an idea of what is the statement of this rule and some very rough idea of how you can prove it. Okay, so what is the Littlewood-Richardson rule? It's a rule which allows to compute the product of two polynomials which have some specific property. And it's proved by executing symbolically some algorithm on the concatenation of two words. So really, I'm going back and forth between algebraic identities, computing with polynomials, computing with concatenation of words, which is the three monoids, and executing symbolically some algorithm, which this algorithm is, you will see, is related to the longest subsequence problem. So really, I'm doing both algorithm and algebra at the same time. And to illustrate that, here is the map of my library. So what is at the bottom in brown is just support, let's say infrastructure. Blue is combinatorics. Red is algebra, and there are few side results which are not related to Littlewood-Richardson rule, which appear in green. And it's a few thousand lines of codes. So let's try to give you an idea of what it is about. So I consider n variable, which in the example would be A, B, C, D. And I consider polynomials in all those variables. So here is a polynomial expression. And I say that a polynomial is symmetric if it is invariant by permuting the variable. So for example, if you look at this polynomial and if you exchange A with B, then A square B will become EB square. A square C will become B square C, and AC square will become BC square, and so on. So that's two examples of symmetric polynomials. And and I will define a specific basis for those polynomials. And basically, my rule is how do you compute the multiplication is this basis? So something quite elementary, let's say. But the proof is not elementary at all. To have a basis, I need some combinatorial ingredient. So the most important ingredient is the notion of integer partition, which is just you take an integer and you try to decompose it as a sum without taking care of the order. So this is a decomposition of 12. This is another decomposition. And actually, there are lots of decomposition, 77. And we call that a partition. So since the order is not important, we sort them decreasingly. And there is a notion for the sum and the length of a partition. And for reasons which will appear later, we love to draw partition by box diagram. So this is the partition 5, 3, 2, 2, which is a partition of 12. So this is a diagram with 12 boxes, which are arranged 5 boxes, 3 boxes, 2 boxes, 2 boxes. And I'm using the French convention. Usually the English draw those diagrams upside down, if you're familiar with those. Okay, let's talk a little bit about formalization. I want to formalize this notion, and I'm following the idea of small-scale reflection. I will comment about that later, which means that when I'm giving a combinatorial definition, when I can do that, I'm giving a predicate which computes the definition, which answer true or false, because I will comment about that. And then using this reflect statement, I'm giving some statement which is equivalent in this case, which means that the last element of the partition is not 0 and the partition is decreasing. The nth element of the eth element of SH is larger than the eth plus 1. Okay? So that is integer partition. And that's my main object, so please don't try to read the definition. So that's a definition which is due to Cauchy and Jacobi. I define a polynomial by the quotient of 2 determinants. Since determinants are anti-symmetric, the quotient is something which is symmetric, and it appears that the quotient is not a rational function, but an actual polynomial. Here is an example. Okay? And this basis is extremely important. So the first claim is that this is a linear basis of symmetric polynomials. Any symmetric polynomials is a linear combination of those polynomials. And since this is a basis, it makes sense to compute the product in this basis, which means if I have 2 such Schur functions, I can decompose their product in Schur function, and there are some coefficients. And it happens that those coefficients are integer, positive integer, which is very important from the combinatorial point of view. If they are positive integer, they are counting something. And that's my point. There is a small comment which, okay, let me skip that. It's not at all very important. So if we look at the history of the Littlewood-Richardson rule, the statement was in 34, and it was the first wrong proof. And actually, it was also the first wrong example. Even the example they give in the paper was wrong. They claim that some coefficient was, if I remember correctly, 22, and it was actually 24. They missed two elements in their enumeration. And I don't know, maybe 6 or 7 wrong proofs were published before Schutzenberger came with the first proof in 77. And all those proofs were published, accepted, and everyone was convinced that the result was proved. Okay? And yes, there is this funny comment by Gordon James, which says that the Littlewood-Richardson rule helped to get men on the moon, but was not proven until after they got there. I'm not sure it really helped to go to the moon, but it's a rule which is really pervasive in mathematics and even in science. So here is a sample of application of this rule. The first comment is that computing Littlewood-Richardson coefficient is something which is sharp P complete. So if you're not familiar with sharp P, is the counting version of NP. When you have an NP problem, you're supposed to answer yes or no. With a sharp P problem, you answer an integer. But that's the same idea. So which means that modulo something like P equals to NP, there is no better way to compute those numbers than enumerating the solution of a combinatorial problem, okay? Because of that, it's appears in Murmulé geometric complexity theory. And okay, I'm not reading all the application. It's just to convince you that those are very, very fundamental numbers, and they even appears in quantum physics or chemistry. So, okay. So how do you compute those numbers? So I need this notion of Young tableau. So this is a partition. This is 753. And I want to fill the box with letters. And the rule is that it should be weakly increasing along rows and strictly increasing along columns. Okay, and there is this notion of row reading, which is the natural reading of the shape. I don't know, sorry, it's in the bottom of the screen for those which are. So I'm just reading the boxes in their natural orders, and that gives me a word, okay? So this is the formal definition of a Young tableau. Again, I'm giving it as a Boolean predicate. And actually, I'm first giving a definition of dominate, which means, is it allowed to put two rows on top of each other? And then if I have a sequence of rows which is ordered by domination, this is a tableau. Okay, this is my definition. And let me redefine in a totally different manner those Schur function, which were the quotient of the determinant. So now I'm taking a partition. Those are my variables, and I'm computing all the way to get a tableau with A, B, and C with this shape. So there are 8 ways, and now for each ways, I'm just counting how many A, how many B, how many C. This gives me a monomial, and I gather that in a sum. And you can see that there are 2 possible tableaus of this shape, and so there is a coefficient 2. It's not at all obvious from this definition that those polynomials are symmetric, but they are. Actually, they are the same as the one I previously defined, but I only will prove that at the end using a specific case of the Littlewood-Richardson rule. Okay, so that's the definition. Maybe, sorry for those which are at the back, but so I'm defining a sigma type for tableaus of a certain shape, and this is, I'm giving it a mathematical component structure of a finite type, which means I'm really giving to Coq a way to enumerate all the solution. And then in this definition, I'm defining just a multivariate polynomial by the sum of all tableaus of the product of et cetera, et cetera. Just a translation of whatever. So this is there is a technical condition. I don't want to give you this definition if I'm asked. Okay, so that's how you compute the Littlewood-Richardson coefficients. So you have 2 partitions, which is the 2 polynomials you're trying to multiply, and one at the top, which is the result. Because of degree property, it's the sum of what is at the bottom must be equal than the sum at what is at the top. I'm multiplying polynomials, so degree should add normally. And here is the rule. So this partition is the outer shape. So here I have 5 boxes, 4 boxes, 3 boxes, 2 boxes. And this is the inner shape. So I just cut 3 boxes, 3 boxes, 1 box. And now I want to fill this, respecting the tableau condition, so increasing in rows, increasing in columns, with 4 zeros, 2, 1, and 1, 2. And there is this extra condition, which is Yamanouchi, which roughly means that if you read the thing backward, at each steps, you have more 0 than 1, than 2, than 3, than 4. So it's kind of complicated intertwined condition. And so those are 3 examples. And actually, because polynomials are commutative, those two, I'm just multiplying 4, 3, 1 by 4, 3, 2, 1 in one sense, in one order and in the other order. So those two results must be equal, but it's not at all obvious that there are as many as solution here than solution here. So there is a bijection, but it's really not obvious that those two numbers are equal from this definition. Let's keep let's keep a little of all those statements. I'm just expressing that. And then the main theorem is what is at the bottom of my screen. If I multiply schur of P1 by schur of P2, I get the sum of over all partition of shape with D1 plus D2 boxes. So sorry, I should have written that D1 is the number of boxes in P1 and D2 is the number of boxes in P2. Of course, P1 must be included in P, and there is this coefficient times the Schur function. So that's my main result. And how is it proved? It's proved using the longest increasing subsequence problem. I will give a little detail here. And so there is a bijection between word and pair of tableaus. And this bijection, actually, we prove that it's computing a normal form in a quotient of the free monoid. So here is really where algorithm and algebra are linked together. We have an algorithm which computes a normal form for a monoid. And thanks to that, I execute symbolically this Robinson-Shenstedt algorithm on the concatenation of two words, and I get my proof. This is the detailed outline of the proof, but I won't I won't read it because it's too technical. Let me just give a little bit about what is this increasing subsequence problem. Let's pick a word and try to get an increasing subword. So subword, you delete some letter, and you want something which is increasing. In this case, A, B, B, D. It's ending in A, B, 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 B. It's also increasing. And what I want to compute is the maximal length of such an increasing subsequence. So something quite elementary. And here is the algorithm to compute that. You start with an empty row, and you insert one by one the letter of the word in the row, following that rule, following the two rules. If there is a letter in the row which is larger than the letter you want to insert it, you take the first letter, which is larger, and replace it. If there is no such letter, you simply append your letter. So for example, if I have this tableau, A, B, C, I want to insert A, so the first letter which is larger than A is this B, and I'm just replacing it. And in this second rule, if in this word I want to insert a B, there is no letter larger than B, so I'm just appending a B. And the specification is that you can prove that the ith entry of your row is the smallest letter which ends an increasing subsequence of length E. So that proves your algorithm, and that's what is stated in formally there. Okay. Yeah. So there is a way to record. Okay. So first of all, sometimes you're replacing a letter here. And if you don't want to lose any information, then what you can do is to insert the letter in a new row which is on top, and then you get the tableau. And there is another remark is that if you record the order in which the boxes are added, you can inverse the whole process and recover the word which you had at the beginning. So this is a bijection, okay? And the crucial point of the proof is to use this bijection to lift the definition of Schur function, which were commutative polynomials, as non-commutative polynomial. And if you have non-commutative polynomial, then you're just concatenating language. There is no multiplicities, and you only prove things using inclusion of sets. There is no multiplicity. Anyway, that's the idea of the proof, but okay. So it's time to go to some conclusion. So first, I presented everything in terms of polynomials, but there is an isometry which is due to Frobenius, which allows to translate everything which was proved in the language of polynomial, in the language of character theory for the symmetric group. So I did this translation, and you have those two statements. And in particular, this means with these statements that I really have an implement a program which computes in Coq the character table of the symmetric group. So, and it's really something that we love to do when we do algebraic combinatorics, is to take some abstract computation like character and translate it in really concrete elementary objects like polynomials, like number and things like that. So that's really typical of my field of research. So conclusion for combinatorial lists. First, it's feasible, which was not at all obvious when I started that. In particular, it was my first development in Coq, so it took quite a lot of time, 6 months of my time. And it proved that Schutzenberger proof, the one which was published in 1977, was correct. And not all my colleagues was convinced that this proof was correct. So now, and also for that, I get a certified implementation. So now I can compute those numbers, even in Coq itself, and get number as large as a few thousand in Coq. Okay, so that's the conclusion for, there is also a further comment for combinatorialist, but I keep it for in my second conclusion slide. So what are my conclusions? First, small scale reflection is really something which is useful when you're doing combinatorics. When you're doing combinatorics, there are lots of particular cases in your algorithm. Those are those which are false when implemented in Sage or in C. All the trivial case, the empty permutation, all the empty objects. And having the system dealing automatically with those trivial cases really help you to focus on what you want. Another comment is that, so this, for me, this is starting to be some old work because I finished formalizing everything even before the COVID crisis. So in the meantime, mathematical component had evolved. And at that time, extending the algebraic hierarchy was very hard. And now they have a tool which is called Hierarchy Builder, which is a game changer. It's quite easier to extend the algebraic hierarchy. They still have improvement in terms of error message, but the tool works. Thanks to the mathematical components basis, formalizing algebra was relatively easy, where formalizing combinatorics was much harder. And one of the reasons I feel is that because in algebra, there are a lot of generic things you can reuse. In combinatorics, I don't see very how to reuse things. So, however, there is something which was not so helpful. So, mathematical component is very oriented toward finite things. In particular, all sets are supposed to be finite, and if you want to deal with finite set, you must be inside a finite type. So it was not so good for combinatorics. And one thing which is really striking. That's my okay. That's okay. Is that when you read the paper, there are lots of cases where the definition, the combinatorial definition, which is given in the paper, is not the one which is used in the same paper. I have lots of examples where you define something with some diagram of box with some properties, and then if you read the paper, that's not the definition which is used. And we do that every time. That doesn't help formalizing. And finally, since my goal is to extend computer algebra system, I tried to estimate what I've done. So my estimation is that I formalize 5% of what is in SageMath about symmetric function character of the symmetric group. This is, okay, you have the number. So which says that if we want to formalize all the Sage combinatorics library, we need something like 50 millions of line of code, which somehow stopped my... Thank you for your attention.
Thank you very much. This is a great talk. We have time for some questions.
Surely you didn't take the number of lines of code for this and then multiply by how many things, because there would be so much overlap, right? So,
why would there be more overlap in proof than in computer algebra?
For proving the things that you have in the Sage library, won't you have lots of overlap in your formalization? You'll use some lemmas in the formalization that you've already proved for other things, no?
Yeah, sure. But I mean, when you're developing a computer algebra system, if there is a function, you can also reuse. So I'm not sure. I see, okay.
Yes?
Yeah, thanks. So what, when you're talking about developing a computer algebra system, obviously things like SageMath are very optimized, right? So maybe, I don't, okay, not having used them. So what, okay.
We want to be expressive, but we are not so fast.
Okay,
really.
So is working in Rocq, is this, do you think this is actually like scalable and could, be used as a computer algebra system, even if it's less efficient in some ways?
Yeah, I mean, that's more or less what I'm trying to do, yeah.
All right, any other last one? Actually, I think we're pretty good on time, so let's thank our speaker again.